Our first topic for today is learning how to combine resistances that are electrically connected in series. In order to facilitate this, we're going to look at the single loop circuit that I've drawn on the board here, which contains a voltage source that is electrically connected in series with a number of resistances. Okay? Because this is a single loop voltage source, the first thing that I'm going to do is I'm going to define the current that flows through all of these elements since they're all connected in series. Since I know my source should be supplying power to the resistive network that it's connected to, I'm going to draw my current as follows. The current's going to be leaving the positive polarity terminal of my voltage source, and it's going to be flowing through all of my resistors. I'm going to label this current I. Now, since I'm going to be using Kirchhoff's voltage law, I am going to assign a voltage drop to each of these series resistances. So I'm going to call the voltage drop over resistor R1, VR1, and I'm going to choose to put its positive polarity reference on the left-hand side, like so, such that the current is flowing into the positive polarity terminal, and thus the resistor is absorbing power. I'm going to go ahead and put my negative polarity terminal over here on the right, and then I'm going to do a similar thing for all of the subsequent resistors. So I'm going to have VR2, positive polarity on the left, and over here, VRN, positive polarity on top. Now, I can write a Kirchhoff's voltage law equation around this loop. So I could say negative Vs plus VR1 plus VR2 plus VRN is equal to 0, where I've simply followed my current around this path, starting from the bottom left-hand corner and ending at the bottom left-hand corner. I'm going to isolate my source to be on one side of the equal sign, and my voltage drops for all of my resistors to be on the opposite side of the equal sign. In doing so, I get Vs is equal to VR1 plus VR2 plus VRN. This looks like what you learned in your Engineering 120 class, which said that the voltage rises due to sources were exactly equal to the voltage drops caused by resistors in a circuit. I'm next going to use Ohm's law in order to express those resistor voltage drops in terms of that common current I that flows through all of the circuit elements. So if Ohm's law says that V is equal to I times R, then VR1 simply becomes I times R1, and so forth. VR2 becomes I times R2, and VRN becomes I times Rn. Now, all of these resistor voltage drops have a common factor of I, so I'm going to go ahead and factor that out, which leaves me with I multiplied by the quantity, R1 plus R2 plus Rn. From this result, we can see that this voltage source here on the left doesn't really see individual resistances, okay? The current is flowing through what we're going to call an equivalent resistance that is simply the algebraic sum of all of these resistors connected in series. So we could take one last step here and write this as I multiplied by REQ, comma S, where the subscript comma S is being used to denote that all of these resistors are connected in series. From this, we can then define REQS to be the sum of resistor R1 plus resistor R2 all the way out to resistor Rn, or using summation notation, the sum from I is equal to 1 to N of Ri. So using this concept of equivalent resistance, we can actually simplify our original circuit to something that's a lot more compact. I have my voltage source, Vs, and it is going to be connected to a single resistance, Req, comma S, and we would actually observe that the same exact current I flows in both networks. So these two networks, the representation on the top with an infinite number of connected resistances, and the representation here on the bottom with a single equivalent resistance, are what are known as electrically equivalent, a topic that we're going to cover in much more detail in the coming weeks.